Okay. Got it. Recorded. Don't tell any secrets, Tammy. No. Okay.
I'm going to tell you all my secrets, actually.
All right. Okay, great. Okay, thank you so much. Okay, Tammy Ma.
Okay, well, thank you so much, Steve, for the invitation. He's got you guys up on video for me to see too. So that's pretty exciting. It's not just, black box. Let me just say that Steve is one of my favorite people to run into at conferences, and I love being introduced to you guys. He does a great job of growing our field and getting some of you guys excited and involved in research. And so, from the entire community, Steve, thank you for all that you do. So as you said, today my talk is going to be about creating a star here on Earth. And I'm going to give you an update on our inertial fusion experiments on the National Ignition Facility. Now, your generation in particular is very familiar with this existential problem that we now have to face and deal with. That is that not only do we use a lot of energy now, we know that worldwide energy consumption is projected to increase something like 33% by the year 2040. So, that's only 20 years away. We have to find a way to both develop new energy sources so that we can keep up our standard of living and hopefully bring some third world countries up in their quality of life. And that's all tied to energy resources and our usage of energy. And then, of course, this leads into the problem of, how do we actually provide for that energy? Well, currently, our three main sources are coal, oil, and natural gas. The relative sizes of these figures that you have on your screen are the relative fractions of how much energy they produce that we are capable of harnessing and using to feed our lifestyles today. And so people always say, well, what about the clean energies? What about wind? What about solar? Well, if I similarly plot those two sources of energy, you can see that they make up a much smaller fraction of our overall energy resources in the world currently. Now, of course, you all well know that coal, oil, and natural gas are carbon sources. So they burn carbon sources of carbon fuels that typically have to be dug up from the earth. And the issue with that is not only does it take millions of years to generate that source of energy, when you burn them, it contributes to global warming. So the question is there another answer, right? And I pose this: could we actually build a miniature sun on Earth and use that to provide significant carbon-free energy for humankind? And that energy that powers the sun is fusion. And fusion energy is attractive for many reasons, actually. First of all, it is safe. What we mean by that is fusion is really, really hard to do. In order to initiate a fusion reaction, you first have to put in a lot of energy to get the reaction going. Because what you're going to do, and I'm going to explain this in a little more detail later, is actually push two atoms together and get them to fuse, and with that release energy. So it takes a lot of external energy to get that reaction going. So if you ever want to stop a fusion reaction, that's pretty easy. It's pretty hard to get it going in the first place, right? So you just cut off that external energy source. It is carbon-free. Carbon is not going to be a byproduct of the candidate fusion reactions that we're interested in. It is sustainable. We know how to obtain the fusion fuel that we need without damaging the environment. And then base load. It's envisioned that fusion power plants would be on the size of our standard kind of gigawatt coal power plants today. capable of feeding large cities like San Francisco and New York City. Energy security. If we can demonstrate fusion as a viable energy source, no longer would we have to be quite as reliant on these foreign oil imports. And so for the US, it's very important for us to research this and make fusion a possibility. And finally, there's no geologic storage associated with fusion. There is no high-level nuclear waste that is generated as a byproduct of fusion. So there are at least 3 ways to achieve nuclear fusion. The first you are very familiar with. This is just the sun. Fusion in the sun is done via gravitational confinement, just the huge size of the sun and gravity holds it together and allows fusion reactions to actually occur. Now, each of these fusion schemes I'm going to talk through exist in a very different parameter space of density, temperatures, and confinement times. So the density of the sun is very, very high, 10 to the 4th times solid density. It's actually relatively cool, a keV. So that's a 10,000 degrees Celsius. And then, 10 million degrees Celsius. Can't do conversions in my head. And then confinement time, 10 to the 5th years. What we mean by that is how long it typically takes radiation to actually escape from the center of the sun all the way to the outside. So the sun is this big, huge thing that is held together by gravity, and it's hot and it's dense, and fusion has time to actually occur because it's so big. So here on Earth, to do that, we have magnetic confinement and inertial confinement. Magnetic confinement, this is facilities like tokamaks, stellarators. Some of you may have heard about the ITER project that is being built in France right now. Magnetic confinement holds together plasmas via magnetic fields. So the densities here are very low density, solid over 10 to the 8th, very hot, 10 keV, and we hold the plasmas together for something on the order of seconds. The third scheme is called inertial confinement fusion. And in this case, we'll concentrate on using lasers to do this. The density here is very, very dense, very, very hot. And then because it's so dense and so hot, if you guys remember from probably high school physics, it means your pressures are going to be very high, right? PV equals nRT, N's your density, T is your temperature. Because your pressures are so high, it is very difficult to hold it together for very long. So in this case, we are talking about confinement times on the order of tens of picoseconds. For reference, the human blink of an eye is actually milliseconds. So milliseconds is 10 to the minus 3. Picoseconds is 10 to the minus 12 seconds. So that just gives you an order of magnitude. So today I'm going to be talking about inertial confinement fusion. And the way we do this is by using high power lasers to drive a spherical implosion. There are 2 main schemes in what we call ICF. The first, let me talk about direct drive. In direct drive, what you're going to do is have a little fuel capsule, and then you are going to spherically irradiate it with lasers directly on your fuel capsule. And these lasers are basically bunches of photons is what lasers are, right? And then you use that pressure, that light pressure, to do the compression of your fuel. There is an advantage if you think about direct drive, is you're going to directly take laser energy to do your compression and heating. So you're going to have relatively high, what we call coupling efficiency. And reduced laser plasma interaction effects. And I'll talk a little bit more about this later. But this is basically the bane of every plasma physicist's existence. The other scheme is what we call indirect drive. And the idea here is instead of shining your lasers directly on your fuel capsule, what you're going to do is have your capsule sit in the middle of a metal canister. This canister is what we call a Hohlraum. It's a German word for empty room, empty space. And the idea is you're going to bring your laser beams in, hit the inside wall of that Hohlraum, and then generate a very energetic flux of X-rays. And then you use those X-rays to do your fuel compression, your capsule compression. The advantages with indirect drive are you have relaxed beam uniformity. It's a little bit less important exactly where you point those laser beams, exactly how uniform that laser spot looks like when it hits your target, and then reduced what we call hydrodynamic instabilities. And again, I'll talk a little bit more about that later. Now, in either case, once you transfer energy to your fuel capsule, the reaction becomes the same. What happens is you're going to have a shell, an ablator, and that shell gets blown off in a rocket-like reaction. And as it's blown off, to conserve momentum, the rest of the shell compresses inward very, very fast at about 300 kilometers per second. Then your fuel core that sits in the middle, and this is going to be deuterium and tritium. These are isotopes of hydrogen, a heavy hydrogen that we're going to use for our fusion fuel. That fuel core is going to reach about 20 times the density of lead and 100 million degrees Celsius. And if you do it right, you spark a little burn right in the middle of your fuel, and that burn then spreads through the rest of your fuel, and you get many times the energy out that you initially put in. So how do we do this? Well, at the National Ignition Facility, the NIF, we are building our own miniature sun. And this facility sits at Lawrence Livermore National Laboratory. We are one of 3 nuclear security labs in the US. We're a sister laboratory to Los Alamos National Lab, which you might have heard more about because that's where we actually did the Manhattan Project. And Livermore, Lawrence Livermore, is about 50 miles east of San Francisco. I actually grew up in the Bay Area, so I got to stay close to home working at the NIF. But for me, I was very fortunate to come on board just as the NIF was completing construction and we started experiments. And that was in about 2009, 2010. So I have actually gotten to grow up with the NIF per se. NIF, turns out, is the world's largest and most energetic laser system. It is housed in a building the size of 3 football fields side by side, and I apologize, I had to represent our California teams on there. The building is also 10 stories tall. It houses 192 separate laser beams. Each one alone is close to one of the most energetic in the world, and combined they produce or deliver, an energy of 1.8 megajoules. So remember that number because I will be able to frame our results, our recent results, in reference to that. The power output is about 500 terawatts. That's actually 1,000 times the power of the entire US electrical grid. So you're like, well, but how come when the NIF takes a shot, the lights across the US don't flicker, right? That is because what is power? Power is defined as energy per unit time, right? So what we're going to do is take a huge amount of energy and then compress it down into just nanoseconds, so that when we release all of that energy into the laser and the laser fires, the total amount of electricity we calculated that it took to shoot the lasers is only about $14. So if you count it that way, it's not a huge amount of energy, but we're compressing it all down so that your energy densities actually get huge. For the laser fans out there, this means the laser is a frequency tripled neodymium glass. Wavelength is 351 nanometers, so UV when it hits the target, pulse length of about 25 nanoseconds. And if I take the roof off the facility, you can have a look inside. The building is as big as it is because we need to house all of these optics that we're going to use to amplify the laser up in energy. And then what we do is we take all 192 laser beams and then we concentrate it onto this tiny target that you see held up to a human eye. This is the hole ROM, that gold canister. Here's one of the holes that the lasers are going to come in. There's a hole on the other side, and you can't in this picture actually see the little capsule that sits right in the middle, but it's there. So let's dive a little bit deeper into the physics. The NIF uses this laser-driven hole ROM to compress the fuel pellet to achieve the conditions for ignition. So this hole ROM that I've talked about, we often call it an X-ray oven. It's gold or sometimes depleted uranium. What that means is it is a high Z material, a material that is high up the periodic table. And the reason you want to use such a high Z material is because you have a more efficient conversion of laser energy into X-rays. Why is that? Well, because what you're going to do with those lasers is when they hit the inside wall of your hole ROM, it starts interacting with that material. The higher up the periodic table you are, the higher Z your material is, the more electrons there are, right? So the lasers directly start interacting with those electrons, and as those electrons transition in their different atomic states, that's how you release a bunch of X-rays. Cool. Okay. But why gold or depleted uranium? It just turns out that those are materials that are relatively easy for us to work with, manufacture, and shape, right? Okay, great. So here you see half our laser beams coming in the top, half through the bottom. The capsule sits right in the middle. How do we actually hold the capsule inside the hole ROM? Turns out what we do is we build that hole ROM in two halves. We put a very thin membrane across the two sides, and we clamp the capsule in the middle. And I'm telling you this because you're going to find out later that these engineering features, like that tent, that membrane, and the fill tube that we have to stick into one side of the capsule, because we use this fill tube to actually fill the capsule with the fusion fuel, the deuterium tritium, right before the shot. These engineering features, turns out, cause us a lot of issues, and we actually have to deal with them in our target design. That fuel capsule consists of an ablator surrounding DT, ice, and gas. So our ablator can be different materials. We experiment with different materials, typically plastic, what we call high density carbon, which is a fancy way of saying diamond, or beryllium. You will notice that these particular materials are low Z. They consist of elements that are low down the periodic table. Why is that? Well, it's because they are light elements. And so we can actually accelerate up our fuel capsule. We can ablate more efficiently, and then we can drive it in faster because they are these light elements. Because what we're going to try to do is actually compress the fuel that sits in the middle, the deuterium and tritium, the two isotopes of hydrogen. And what we do here is we want to put the DT as a gas in the middle, gas because it's more compressible. However, if we just fill it with gas, we don't actually get enough fuel packed in there. So what we actually do is also grow what we call a cryogenic DT layer. So it's deuterium tritium ice. So just like water ice, but pure deuterium tritium. And that's how we can pack enough fuel in there such that what we're going to do is do this compression, and it is spherical, so we can turn 100 million atmospheres of pressure via a spherical compression into about 300 billion. And what we're going to do is compress the fuel capsule that starts out at about 2 millimeters down to about 50 microns. So just for reference, a human hair is typically around 100 microns or so. So about half the diameter of a human hair is what we have to compress down to. And this is difficult for a number of different reasons. Not only is the convergence ratio really huge, right? You're going from a really big size down to a small size, but it's really hard to do this symmetrically. So you can imagine if you're holding a balloon in between your fingers and you were trying to compress it, right? Everywhere it could, that balloon would push back out. So even if you got your friend's hands with you to try to compress the balloon, you would still have trouble doing it spherically symmetric, right? And so that is the name of the game. If you cannot compress spherically, you're actually going to waste the kinetic energy and not efficiently turn it into heat. So that's the name of the game. Okay, so I'm going to play a video, and I'm going to narrate over it, and hopefully it streams okay. Sometimes the refresh rate of these virtual programs doesn't work quite as well, but let's see how it goes. So we're going to start in the NIF control room. When I'm running my experiment, this is where I spend my time.
4, 3, 2, 1, shot.
So first, the laser is going to be born in the master oscillator room. It's born as a fiber laser at a nanojoule level. And here we're going to shape it in time. And then we're going to split it 48 ways and send it into the pre-amplifier module, where it bounces around about 100 times, gets amplified up to the millijoule level. At this point, each of the beams gets split another 4 ways and gets sent into the main amplifier. And there it bounces back and forth 4 times across that enormous football stadium size facility that is NIF. And now we're going to follow along with some single beams. And you can see at this point, each of these lasers is a square, about 40 centimeters by 40 centimeters. And the reason the laser is so big is because we have to actually spread that energy out as it travels through the optics, so we don't actually damage the optics themselves. Now the lasers are going to approach the target chamber. Half the beams get sent up, half get sent down. We're going to frequency convert from red to green to blue light. And as we do that, you can see that the lasers all sync up. And now they are incident on that tiny target that sits in the middle of the chamber. Laser beams coming in through the top and bottom laser entrance holes, hitting the inside wall of that hole ROM, generating that very energetic flux of X-rays. The X-rays start ablating that fuel capsule. And then the rest of the fuel compresses inwards and heats up. And if we do it just right, this is what we call ignition. More energy out than we put in with the lasers. That is the name of the game. So, like I mentioned, the NIF came online right around 2009. So we've been running about 2010. So we've been running about 11-ish years now. And if you follow the news and the science news, you would have seen that we recently had a very big breakthrough on the NIF. And I'm going to walk you through the history of our experiments on the NIF that got us to this point. And let me just add that the NIF actually builds on about 60 years of research before that. At Livermore alone, we had a series of different lasers growing in size and growing in the number of laser beams since the 70s, basically. So But I'm just going to talk about the history of our experiments basically on the NIF. So what I'm going to show you is a series of plots. On the left is fusion yield versus time. And on the right, I'm going to show you how our shots performed in terms of hotspot pressure. Remember, we talked about NKT, right? Density times temperature, versus how much energy we were producing through fusion. And I'm going to call that hotspot energy. So that's the x-axis. Of course, to get to ignition, you want to have high pressure and then generate a lot more energy right back out from the hotspot. And so we want to move up and to the right. So we first started experiments in 2009, 2010. The shots I'm going to actually plot out for you are only the ones where we use deuterium tritium fuel. These shots are expensive, complex. It takes us 3 to 6 months to prepare every single shot, even though we are shooting every day on the NIF. And so what we'll do is a series of experiments where we test out different things before we do an integrated shot with DT. So we're only going to plot the results from the DTs here. Between 2010 and 2012 was what we called the National Ignition Campaign. We were using a design that had been developed with computer simulations, because until the NIF was built, we couldn't actually test at this scale. So we had to rely on our computer simulations that modeled the physics, that folded in experiments from the smaller laser, but obviously didn't quite get everything right? And you can see that our fusion yields were quite low at that time. We weren't able to generate a lot of fusion reactions. And the reason why, and this is a 3D computer simulation done here at Livermore on the supercomputer, the whole other talk that we could go into some other time. But what you see here is you expect this spherical compression to generate this nice clean hotspot. And obviously this hotspot isn't even round. And all of these like jets of material that you see here represent what we call hydrodynamic mix, like the ablator, which was plastic, getting mixed into your deuterium tritium, your hydrogen. So when you mix like something high Z into something low Z, you basically quench the burn and you can't get very hot. We found out that we just actually weren't very symmetric. We were having a lot of trouble generating a uniform X-ray flux that could keep our implosion round the entire time. So that was our issue up until about 2012. Then we figured out how to improve the stability with what we called the high foot campaign. What we did here was we didn't try to drive our implosions quite as fast. We thought, we'll take it easy. They can go a little bit slower. Hopefully they'll be a little more robust. And you can see that we got up to 10 to the 15 neutron yields for anybody familiar with neutron yields. But basically market improvement up to about 30 kilojoules in fusion yield that we were generating. That campaign lasted about 3 years. Then after that, we switched over to using diamond ablators rather than plastic. What we found there was with a diamond ablator, because it's higher density than plastic, right? That's what diamond is known for. We could make the implosion go faster, with similar laser energy. And diamond was a little more efficient because of its density in absorbing that energy. So what we could do was actually put it in a bigger hole ROM than we had used previously. And that gave us a little more flexibility to point the laser beams to slightly different places, et cetera, and could give us a more uniform implosion. So you can see it's still pretty ugly, but it's a lot rounder than it was before. After that, we tried new laser and hole ROM designs that could increase the amount of coupling. We can more efficiently couple that laser energy into X-rays into drive energy. And a couple of other improvements in the shape of the whole ROM, the relative sizes of the capsule and the whole ROM, et cetera, et cetera. That got us up to over 100 kilojoules of fusion yield. Then more recently, we figured out ways to mitigate the degradations that we had. I had mentioned the tent, the membrane that we use to hold the capsule in the middle. I mentioned the fill tube that we use to fill the capsule with the fuel. Both of those things were causing asymmetries in the system before the implosion even started, basically. And we found ways to improve those features. And we brought the fill tube down in size by about a factor of 5. And so we ran into all kinds of issues, of course, where we went from a 10 micron fill tube down to a 2 micron. And again, a human hair is 100 microns. And so, we were breaking targets all the time and issues like that. But eventually, that brought us, we were able to most recently do a shot that got us to over 1.35 megajoules. And so remember, I told you to actually remember the number 1.8, right? That was the laser energy going in. And actually, to be fair, on this particular shot, it was 1.9 megajoules going in because we've improved NIF in the 20 years since it was built. But anyways, we got 1.35 megajoules back out. And that is just enormous if you think about the relative ratios of the energy produced versus the energy you put in. So we are very, very close now to that ignition threshold. And just as a comment, over these 10 years of shots, this was just 171 experiments. So it was a huge amount of progress in a very small amount of time. And this, of course, is not just a project here at Livermore. We have collaborators at the other national labs, vendors that we have to buy products from across the US to bring together this incredibly complex engineering project. And so I am actually very tired because the past few weeks, we've been coordinating a series of briefings to actually tell the world about this huge result. And what's really exciting is these recent game-changing results on the NIF then lay the groundwork for inertial fusion energy. So if you've been able to actually read about this result, all of these articles then start talking about how we could use fusion as a path towards clean energy and help to fight climate change. Now, the NIF itself is a scientific facility. The goal of the NIF is purely to demonstrate that this is a scheme that works, that you can get to ignition. And then for some of our other research, we need to generate very, very high neutron yields. So it is an experimental facility. If we were to turn inertial confinement fusion into an actual energy producing source, what you would need to do is develop a whole bunch of other different technologies, such as the NIF shoots at about 1 shot every 8 hours or so. It is complex. A lot of that time is taken up by needing the lasers to actually cool down. You're switching instruments in and out. We have people that go in the facility to pull film because we still have to record our data on film in some cases. It's a very complex process. In order to have an economical power plant that actually generated enough electricity that it would be worth putting on the grid, you have to not only produce enough electricity to keep the laser itself running, right? You also have to generate enough that you could send a good fraction of it out to the grid. So it's envisioned that a fusion power plant would have to shoot about 10 hertz, 10 times per second. And so inertial fusion energy is going to be a huge challenge for the next generation of scientists, which is why I'm actually talking to you guys, because we're hoping to motivate some of you to join us in this endeavor. Not only do we need a laser that can shoot 10 times a second, which we actually do have now, and that technology exists, you have to deliver a target at 10 times a second that you can shoot, you can track and shoot. You have to develop the materials for the fusion reactor walls. And then you have to develop all of the other recycling technology. If you're going to be shooting tritium, you have to recycle that tritium, for example. So going forward, in order to realize the potential of IFE will require developing new technologies and a whole lot of innovation. Chemical competitive energy source. So it will not be easy, but I am a true believer. I do think this is something the US needs to invest in, and it will be a multi-decadal endeavor. Now, the US is currently a clear world leader in inertial confinement fusion. In France, they are building their own smaller version of the NIF. It's called the laser megajoule. Russia and China have their own projects, but for the moment, they are still probably at least 5-10 years behind the NIF. But what we see is that there are significant investments in those other countries, significant interest and investments. So we do have to continue innovating. And one of those ways is also by not only doing inertial confinement fusion for experiments, but to turn it into an energy source. And I know you guys are undergrads, but it's never too early to understand how science gets funded in our country. It basically our government representatives, Congress people, the program managers, the Office of Science, whatever, they listen to us and they need you to actually advocate for your science and why that science is important. Otherwise, they're not specialists. We are. And so in the next year, there will be several community workshops in inertial fusion energy that are being planned, and we would encourage you guys to get involved just to learn what's out there. And what the community does is we get together and we chart the path forward. We recommend to the nation where we should go and where we should put money. So annoying and fun at the same time. But anyways, fusion energy offers a long-term vision for enduring global climate and energy security. So that is what gets me out of bed every day. I'll also just 2 more slides. Just say that we also use the NIF for what we call discovery science. What we do is we open up the facility every year. About 10% of our shots go to the academic community, and professors all around the world will apply. And with the NIF, not only can you generate conditions similar to stars, we can also generate conditions similar to the center of giant planets, supernova, and you can actually study, you can generate and study astrophysical phenomena in the laboratory. So that's a lot of fun. And we bring in a ton of summer students every year, over 1,000 summer students, even this past year when everything was virtual, to do research, not just on the NIF and on lasers, but in cyber, in computation, in bio, across Livermore. So I encourage you to Google Lawrence Livermore summer student and see what opportunities pop up. And with that, I will just wrap up, and I'm very, very happy to take any questions that you guys might have. Thank you.
Well, thank you so much, Tammy. I'm going to open it up if there are any questions, especially particular students. If you have questions about not only the NIF, but Lawrence Livermore National Lab, or how Tammy actually ended up where she is. So go for it. You'll have to speak up because the mic.
I was just wondering if you could elaborate a little more. I mean, I know this is theoretical at this point, but when at this point, how would you like collect the energy that is resultant in the future? I can't talk. Sorry. I think you know what I'm trying to say.
Yeah, no, I think that's a great question. Yeah, so right now you're right. It's all a little bit conceptual at this point. What we do is we measure the number of neutrons that we generate, and each neutron has a particular energy, right, as it's streaming out. And from that we can infer how much energy we created. In a power plant, which I think is what you're asking, what you would do is you would capture those neutrons in the walls of your reactor, what we call the blanket. Those neutrons would get absorbed, they would heat up the material. There's a lot of different designs. The simplest explanation is just it would be like a liquid flowing wall of lithium. And then it gets hot. And once something is hot, you can extract that heat very conventionally, right? You turn it into steam and then you run turbines. So that is why we actually say that we think a fusion power plant actually fits into our current grid pretty easily, because you're just generating heat, run turbines as usual.
Thank you.
Your other questions? Speak louder.
Does inertial confinement specifically have like a clear path towards energy production? Because like in my mind, I'm thinking you're placing a pellet and then blowing it up and then having to put a new one in the chamber for every shot. Is that one, can that turn into a viable energy source from there, or is that research for other types?
Yeah, so another really great question. I'm very impressed already. Yeah, that is absolutely the challenge of ICF, right? We would have to be, if the lasers are shooting 10 times a second, you have to refresh that target 10 times a second. So that is an engineering challenge we will absolutely have to tackle if we want to turn this into a real energy source. You know, and I mentioned that it takes us like 3 to 6 months, right, to prepare an experiment on the NIF. And a good fraction of that is building these very, very complex targets, right? That's not even a great picture because you can't even see how complex it is from this. So the challenge is how to bring it down in, how do we understand the physics well enough that we can be robust and repeatable, and then make the targets simpler and cheaper as well. And yeah, I expect that will be a huge thrust of the research in the US going forward if we're going to be serious about this. Did I catch your full question? There was a second half that I didn't hear very well, I think.
That was pretty much it. Like the second part was if not, but you kind of seems to go in the direction of that being something that you work that is working toward.
Yeah, I mean, so like with magnetic confinement fusion, you have a far more continuous energy production, whereas what we're doing here is pulsed, right? You have to just keep doing over and over. So there's pros and cons to both. Because we're pulsed, it also means that the components are quite separable. Like we can try different drivers. It doesn't have to be a laser. Maybe you use a different X-ray radiation source, something we call pulsed power. You know, there's stuff where you use a huge beam of ions to do the compression and heating. So there's different things we can try. And by no means is this particular design necessarily the right one for fusion energy. But what we were able to demonstrate is the technical basis that yes, ignition in the laboratory is possible. And so with that, that's what these workshops that we will have going forward will help do, will help us maybe not necessarily down select, but lay out what the main problems are that we need to investigate in our field, in the next few decades.
Okay, any other questions?
This is more of just a clarification question.
Just speak out loudly though, at that mic.
This is just more of a clarification of something that I didn't fully follow, but on the left graph, we have like the blue dash R for like a certain threshold for how much energy and pressure. Can you just kind of explain like why that is where it is?
If I think I heard you correctly, you're asking about these dotted lines.
Yeah.
Okay, awesome. Yeah, so I'm sorry I didn't go into enough detail about this. These dashed lines represent what we call yield amplification of 30x, as in the energy coming out of the fuel is at least 30 times what we put into the fuel. And this is a better scientific term, actually, than the ignition term that I used earlier, which is laser energy. But Congress people understand the laser energy one a little easier. But yeah, so for us, this is primarily the region where we have robust propagating burn, as in you cannot get this type of amplification of energy unless you are burning through a decent amount of that DT fusion fuel. And so in a lot of ways, this is actually scientifically more important than our ignition definition that we use out in the media. And it shows essentially that we're there. We were able to successfully demonstrate propagating burn in the laboratory in fusion.
Other questions? Take a couple more.
I was just wondering, so you've mentioned a couple strategies that you use specifically with the target to maximize your output. I was wondering, are there any interesting new things that you're trying other than the uniform X-ray oven or other strategies that you're using for manufacturing challenges and ways forward?
Yeah, no, absolutely. There are so many exciting new things that we have tried a bit of, and we will probably try more of later. Let's see, let me go back to the very simple, the very simple schematic. There are things we are doing, playing with magnetic fields, where we have maybe a strong magnetic coil around the whole ROM itself. What that does is changes how the plasma moves. It helps with the compression. The Z machine at Sandia, I don't know, you might have seen pictures of it in different places. The Z machine is a pulse power machine, meaning what you do is you have these very thin wires and you send a huge strong current through it. And when you send such strong currents, you generate a magnetic field, right? If you have a bunch of wires in an array, you amplify that magnetic field, and you use the magnetic field to be a compressing force. So that's what we call magnetic inertial fusion. That's the primary scheme. And then there's beam fusion schemes too. You have a beam of electrons, beam of ions, beam of protons, and you use those to heat, compress. So yeah, many different schemes, absolutely. Which means you need different facilities, different drivers, totally different target designs. And sometimes where it gets complicated, you also need a whole different set of computer simulation codes that includes different physics. And so our field is expanding very rapidly for that reason, because there's all of these different schemes, and therefore a bunch of different, small experiments that universities can also get involved in, right? Like just measuring the magnetic field generation that you have. right, in these different configurations, you can do that at subscale, and then put that into your codes, test, see if you were right, and then, scale up to the next big facility and try again. So yeah, absolutely, all different types of target schemes. And this direct drive scheme, at the University of Rochester in New York, they have the second biggest laser in the US right now. It is 60 beams instead of 192. And their beams are set up in a way that you can symmetrically irradiate in this way. And they do a bunch of direct drive experiments there.
Okay, I'm going to ask one question, and then I think we'll end. So Tammy, I recently read an article about, we've had plasma drive in spaceships for quite a while, and people have been working on plasma drive engines. But I read an article just recently that said with the success of the NIF's, the NIF's recent success, that fusion plasma drive was on the horizon, and that we'd be visiting the outer planets in the next 20 to 40 years. What do you
wow.
think about that?
Yeah. Yeah, I mean, a couple of issues there. First of all, fusion's really, really hard. And currently we can only harness it in the laboratory with these very large scale machines. So yes, certainly a possibility that now that we've done it here, right, you start scaling down, you try new innovations, and there's actually a lot of private fusion companies coming online now that are funded through venture capital, trying different things on smaller machines. So a possibility, but it's hard. You also wonder whether or not you want a fusion reactor on a spacecraft, because they're just so complex right now. But that being said, sure, I'm all for it. 20 years seems quick, but maybe 40 is doable. Yeah.
Well, it's 30 years in the future, so.
So we were right.
Well, I want to thank you again. It was a wonderful talk, and I think everyone enjoyed it. And thank you for putting the effort into making it at a level that undergraduates could really enjoy, and we really appreciate that. And let's thank our speaker one more time.
And thank you all for your time and sitting through this lecture.
Thanks. Okay, that's it, and thanks a lot. We'll see you next week, I believe, right, Ann? Okay.
Thank you so much, Steve. Hope to see you soon at APS, maybe.
Okay. I'll talk to you. I see you. Are you going to DTP?
Hopefully, yeah.
Okay, hope to see you there.
Yeah, hope to see you there. Bye.
Okay. Thank you. It worked really well. We're in the almost like she was here.